All right, so in this example, we're working with an ideal Brayton cycle. And so we have air entering a compressor at 70 kilopascals and 15 degrees Celsius. It then enters into a combustion chamber and then it exits out into a turbine. And when it enters that turbine, we have a temperature of 1400 degrees Celsius and it exits the turbine at just a known pressure. So in a Brayton cycle, a couple of properties that you know are, or at least an ideal Brayton cycle, you have P1 equals P4. So in other words, the exit temperature of the turbine and entrance temperature of the compressor should be equal, and that makes sense because they're both atmospheric. And then same thing with either side of the combustion chamber, their pressures are equal. So a few things we're asked to find here. So we're going to start off with the temperature at the exit of the compressor. So in other words, state 2 is what we're looking for, so T2. Now, because we're working with air and we're also told that this is an ideal process or an ideal cycle, we can use the relation of T2 over T1 is equal to P2 over P1 to the K minus 1 over K. And from simple algebraic rearrangement, we can find that T2 is equal to T1 times P2 over P1 to the K minus 1 over K. So now it's pretty much the simple part where you have T2 is equal to T1 is 288 Kelvin. Make sure you're in Kelvin when you use this formula here. And then it's going to be P2 over P1. So we're going to make sure you're in the same unit. So I'm going to use kilopascals. So 1.5 megapascals is 1500 kilopascals divided by P1's 70 kilopascals. To the K minus 1, so the specific heat ratio is 1.4. So you have 1.4 minus 1, and that's for air, obviously. 1.4 minus 1 over 1.4. And this all equals 691.3, and that's going to be in Kelvin. However, you're looking for Celsius, so just subtract 273, and you'll get 418.3 degrees Celsius. Now, similarly, we can use this formula right over here to find the part B temperature on the exit of the turbine. So instead of T2, we'll have T4 as that's the exit, and then the entrance T1 is going to be T3 in this case. So once again, you have T3, or in other words, you have the discharge temperature is equal to the inlet temperature times discharge pressure over inlet pressure to the K minus 1 over K. When you plug in your numbers, you'll have T4, or discharge temperature, is equal to the inlet temperature of 1673. Make sure you're in Kelvin, as you have 1400 up there in Celsius, times the pressure difference or pressure ratio. So P4 is equal to P1, which was 70 kilopascals, and P3 is going to simply be 1500 kilopascals, as we have P3 is equal to P2. And that's going to be, once again, to 1.4 minus 1 over 1.4. And if you plug that into a calculator, you'll have that T4 equals 696.97 Kelvin, or in Celsius, it's going to be 423.97. Next, to find the work of your compressor, you have the work of compressor is going to be equal to H2 minus H1, or in other words, specific heat of air times T2 minus T1. And if you plug in your numbers here, you'll have that the work of the compressor, WC, is equal to 1.005, which is the specific heat of air, and that's kilojoules per kilogram Kelvin, times the temperature difference of T2, which was 418.3, minus T1, which was 70 or 15 degrees Celsius. Because this is a delta T, you can use Celsius or Kelvin, because this plus 273 minus this plus 273 is going to be the same thing if it's in Kelvin or Celsius. So if you multiply this out, you'll have that the work of the compressor is 405.3 kilojoules per kilogram. Now we have to find the work of the turbine. So similarly, the work of the turbine, I'll do it on the left side here. WT is equal to H3 minus H4, which is also equal to CP of T3 minus T4. Now, if we just plug in our numbers here, you'll have that equal to 1.005 times T3, which we have as 1400 Celsius, minus T4, which we calculated to be 423.97, and that is also Celsius. Now, if you plug this into your calculator, you'll have that the work of the turbine is equal to 980.91 kilojoules per kilogram. Makes sense because it's larger than the compressor. And next up's the back work ratio. So BWR, very simply equal to the work of the compressor divided by the work of the turbine. So that's going to be equal to 405.3 divided by 980.91. And that's going to be equal to 0.413, which is also known as 41.3%. Next, we have the heat requirement for the cycle. So we have Qn is going to be equal to H3 minus H2. And you guessed it already, that's going to be equal to Cp times T3 minus T2. So we're going to have Qn is equal to 1.005, the specific heat of air, times T3, which we have as 1400 Kelvin, or Celsius, minus T2, which we calculated as 418.3 Celsius. And plug this into your calculator, and you'll have that Qn is equal to 986.61 kilojoules per kilogram. And last but not least, we have our thermal efficiency of the cycle, which is going to be equal to the work of the turbine minus the work of the compressor divided by the heat requirement. So that's going to be equated to 980.91 minus 405.3. And all of that is going to be divided by 986.61. And then when you plug this into your calculator, you'll have the thermal efficiency being equal to 0.5834, or in other words, 58.34%. So as a recap, I have all of the answers right over here boxed into the question here. So if you have any questions, feel free to ask in the comments, and I'll do my best to answer you back.